Hi everyone, this is Mrs. GA, and today we're going to be graphing logarithms with transformations. Alright, so before we start, I have a quick warm-up where you'll be graphing two parent functions for logarithms, so please pause the video and give these two a try. Alright, go ahead and check your work here. So again, it's really important that you're picking strategic x values that work really well with your base. So here you have that increasing graph, and here you have that decreasing graph. The domain and range is the same for both, and they both have that vertical asymptote at x equals 0. Alright, so now we're going to start talking about how to graph logarithmic functions that have transformations. So luckily those rules for transformations that we've been using all year also apply to logarithms. So what happens if there's a negative, if we're multiplying by a number, if we add or subtract from x, or if we add or subtract from the entire function. So we are going to look at these different transformations in reference to a parent function where the base number is positive. So you can see here b is greater than 1, which is why we have that increasing graph. And we have the asymptote at x equals 0. And the domain is 0 to positive infinity, and our range is all real numbers. Okay, so let's start by looking at these first two, if we add or subtract from x. So both of them are horizontal translations, which remember are shifts. So if we subtract from x, it actually shifts our graph to the right, and that would be h units. So not only would our graph shift to the right, like this, but our asymptote, our vertical asymptote, would also shift to the right by however many units h is. So now our vertical asymptote is now at x equals h. Again, however many units we shifted to the right, and that means our domain is from h to positive infinity, and the range would still be all real numbers. So likewise, if we add to x, it's still a horizontal translation, but this time it shifts our graph to the left, h units. So again, however many units h is, it will also shift our asymptote that same amount. So here our asymptote will actually be at x equals negative h. So whatever this value is, our domain would be from negative h to positive infinity, and our range again is still all real numbers. I'm just going to start writing like this to save space. Okay, so now let's talk about what if we add or subtract from the entire function. So you can see this time it is not specifically grouped with x. So since we're adding or subtracting, it's still a shift or a translation, but this time it's going to be vertical. So if we add to our function, like plus k, it's going to shift our graph up, but it's not going to shift our graph to the left or right. It's kind of hard to tell that it's been shifted up, but just imagine it has. And since it's only been shifted up, it actually doesn't move our asymptote. So our asymptote still stays at x equals 0, and it actually doesn't affect our domain or range. Likewise, if we subtract k from our entire function, it will shift our graph down, so maybe something like this. Since we're only moving down, it doesn't move our asymptote, so our domain, range, and asymptote stay in the same place. So you can notice here, generalization is that only horizontal shifts will move our asymptote. Okay, so now let's talk about what if we multiply our entire function by some value. So here you can see we have that a being multiplied out front. So let's first assume that the absolute value of a is bigger than 1. We call these types of transformations vertical stretch by a factor of a. So really that's just going to make our graph stretch kind of more upward than our original graph. So it might look something like this. Again, it's kind of hard to tell just by looking at the graph, but essentially all of our y values have been doubled. Since we are not shifting left or right, our asymptote remains the same at x equals 0, our domain remains the same, and so does our range. So likewise, if we're multiplying by a value, it's still a vertical stretch or shrink. So if the absolute value of a is less than 1, it's going to create the vertical shrink. Again, we're not shifting anyway, it's just kind of like our graph has been compressed down. So maybe it looks something like this. Again, it's a little bit hard to tell just by looking at the graph. So all of our y values have essentially been cut in half, or whatever the shrink factor is. So since it hasn't been shifted left or right, our asymptote is in the same spot, and our domain and range are the same. Okay, now let's look at what happens if we multiply our entire function, so notice on the outside, by a negative. So remember, multiplying the y value reflects over the x-axis. So instead of having a graph that looks like this, it's going to look like this. There you go. Our asymptote remains in the same place, and our domain and range are still the same. Okay, and then the last transformation you might see is if we multiply the x value by a negative right here, it will actually reflect over the y-axis. So instead of having a graph that goes like this, we are going to have a graph that goes something like this. Again, our asymptote is unmoved, so x equals 0, and our domain and range are, our domain is actually going to change because this time it's everything to the left of our asymptote. So it's negative infinity to 0, and our range is still all real numbers. So you can see that these same transformation rules that we've been working with all year work just as well with our logarithmic functions. So if you understand those basic transformations, you should be able to graph just about any function that we throw at you. All right, let's give a couple of these a try. So here we're going to describe the transformation and then graph it, and then we're going to describe the domain, range, and the asymptote. So for these, it might be nice to start by graphing the parent function. So we can do this really quickly with, we can do two really easy points. We know that our parent function, which would just be log base 2 of x, it goes through, and I'll do it dotted. It goes through the point 1, 0. Remember, it goes through, always goes through 1, 0, and then it goes through whatever our base is, so 2, 1. So our parent function looks something like this. So I would always start by graphing those 2 points. So again, the 2 points you're going to graph, I'll write it up here, are 1, 0, and whatever your base is, 1, b1. So those will be true for all parent functions. Now we're going to look at the transformation. So here I can see that it's going to shift up 3. Shift up 3 units. It's a vertical translation. So that means I can take all of the 2 values we know, and we're simply going to move them up 3 units. So 1, 2, 3, and then 1, 2, 3. So then our graph looks something like this. So again, the dotted line is our parent function, and the solid line is our new function. Since we only shifted up, our asymptote stays in the same place. So our domain is still 0 to positive infinity. Our range is still all real numbers. Let me write that in interval notation again. Negative infinity to positive infinity, and our asymptote is still at x equals 0. All right, let's try this next one. So here we have f of x equals common log of x plus 5. So remember, when you don't see a base, it is base 10. So we are going to start by plotting the 2 points for our parent function. So remember, we're going to plot the points 1, 0, and then b, which is 10, 10, 1. So for this, I'll change the scale of our x-axis to count by 2's. So 1, 0 would be somewhere right around here, and 2, 4, 6, 8, 10, 1. The scale of my y-axis is still by 1's. So again, I'm going to do a dotted line to show that this is our parent function. And then let's describe the transformation we see. So we're adding 5 to x, so that must mean that it's going to shift our graph actually to the left 5 units. So we'll use the points that we know and we'll shift them to the left. So 1, 2, 3, 4, 5. Remember, I'm counting by twos, and then 1, 2, 3, 4, 5. And that gives us, oh, and then we're also going to be shifting our asymptote to the left 5. So it was at x equals 0, so then we'll go 1, 2, 3, 4, 5. So now it's going to be at x equals negative 5. And I would draw that in first, so when you sketch your graph, you make sure not to cross that asymptote. There you go. So since we didn't shift our graph to the left, our domain is a little bit different. Our domain is going to be from negative 5, where our asymptote is, to positive infinity, everything to the right. Our range is still all real numbers, and our asymptote again is at x equals negative 5, because it was shifted to the left 5. Okay, let's look at this next one. So here we have f of x equals negative natural log of x. So remember, this is base e, which is approximately 2.7. So let's start with the parent function. So we're going to plot the 2 points, 1, 0, and then e, which again is about 2.7, so we'll estimate 1. So we have 1, 0, and then almost 3, 1, like this. And we know for the parent function, our asymptote is at the is x equals 0. So now let's describe the transformation. Here we see it's going to reflect because of the negative, and it's going to reflect over the x-axis. It's a vertical reflection. So that means that the 2 points that we know are also going to reflect. Since this point is on the x-axis, it's actually going to stay the same, but this point is going to reflect over and go down to that lower quadrant. So it's actually going to go right down to here. And then we're going to graph like this, and remember, our asymptote is unmoved because we don't have a shift to the left or right. So that means our domain is still 0 to positive infinity, our range is still all real numbers, and our asymptote is still at x equals 0. All right, last one here, we have our base 4 logarithm. So let's start with the parent function, 1, 0, and then we'll do 4, 1. So 1, 0, 4, 1. There's our parent function. Here we can see that we have a vertical shrink. So vertical shrink because the value is less than 1 by a factor of 1/2. So that means all of our y values, because it's vertical, are cut in half. So this one will stay the same because 0 cut in half is still 0. But this value is going to be cut in half. So instead of at being 4, 1, it's actually going to be at 4, 1/2. So right here. So you're actually going to have a graph that looks like this. Our vertical asymptote is unmoved, and our domain and range are also the same. So there you go. So again, we're always going to start with that parent function, and we can use these 2 points, 1, 0, and then our base value 1. And then I recommend actually writing out what you think the transformation is before you sketch it. And just remember, only a horizontal shift or translation will affect your vertical asymptote, which also affects your domain. Alright, so at this point I'm going to ask you to pause the video and give these 4 problems a try. So please use that same process we used in the last example, and we'll check your answers in just a few moments. Alright, go ahead and check your answers here. So remember, the dotted lines are the parent functions, and the solid lines are the new function. So the first one, we're simply shifting our points down 4, so our asymptote stays the same. For the second one, we're shifting our graph to the right 2, so notice our asymptote also shifted to the right 2 along with our points. For the third one, we have 2 transformations. We have a reflection over the x-axis and a vertical stretch by a factor of 2. So imagine we take this point, we double the y value, and then you reflect it. Or you could reflect it and then double it. So this point stays the same, but this point should be at 4, -2. And then the last one, we have two transformations again, left one, up one. So notice since we moved to the left one, our asymptote also shifted to the left one. All right, so that is all for today's video. Thank you guys so much for watching.